Good morning. My name is Vladimir Bulovic. I'm the director of MIT.nano, and I have an absolute pleasure to be a host of today's Nano Exploration webinar. Today's speaker is Jessica Boles. She is a graduate student in Professor David Perol's group and has done some remarkable work in miniaturizing power electronics through piezoelectric energy storage. In a moment, I will ask Jessica to take over, but before I do, I'll just remind you, just as a way of providing the bandwidth to the rest of us, turning off your video and muting yourself is one good thing to do now at the beginning. And then if you have questions at the very end of the talk, we'll ask you to submit them via chat, or if not via chat, raise your hand and I'll call upon you. With that being said, Jessica, please do take over.
Great, thanks. Power electronics are our building blocks for processing electrical energy. Here I'm showing a variety of things that affect our daily lives, where we can go, who we can talk to, how we can live. And all of these are critically dependent on power converters. Now, one big focus of the power electronics field today is figuring out how to make the converters inside of these things much, much smaller. A smaller converter has quite a few advantages that ultimately boil down to reduced cost and a wider realm of potential applications. Now, for those not familiar with power electronics, I first want to introduce the concept of how a converter works. At its root, a power converter pulls energy in from a source, momentarily stores it, and then delivers it to a load in a different form. And for us, that usually means a different voltage. Now, this process is cyclical, which means we do this hundreds of thousands, sometimes millions of times per second. Now, whenever we start to think about making power converters smaller, we often refer to power density, which is the power out divided by the volume of the converter itself. In addition to power density, we also need high efficiency, which is the percentage of the power we bring in from the source that we can actually deliver to the load. Now, high efficiency helps decrease our heat dissipation, which is increasingly difficult to handle as we increase power density. Now, if we take a look at the inside of one of these power converters, we see that a large proportion of the volume is actually taken up by energy storage. I'm going to highlight that in the MacBook charger you see here. Now, in a traditional converter, we would use inductors and capacitors for energy storage, but there's nothing that says we have to. In fact, electromagnetic energy storage scales down pretty poorly with volume. Now, if we take a look what happens to an inductor as we scale it in all three dimensions by epsilon, we'll just call that a scaling factor, like this. Its volume is going to increase by epsilon cubed, but the power it can handle is going to increase by epsilon to the fourth. That means just a small increase in volume gives us a drastic power increase, and that's great for high power applications. But if we look at this in the opposite way, and we see that as we scale down volume, power decreases much faster, meaning our power density is actually going to drop. That's counterproductive for miniaturization. So to enable major advances in power density going forward, we're going to have to look at alternate ways to store energy, such as piezoelectric energy storage. Piezos rely on the piezoelectric and inverse piezoelectric effects, which essentially means that when we apply a voltage to a piezo's terminals, that voltage induces mechanical stress and strain in the material and vice versa. Now, through that process, we can induce mechanical resonance, like you see here in this animation, in which the piezo is storing energy in mechanical compliance and inertia, somewhat like a spring with mass. Now, piezos are attractive from the standpoints of they have planar form factors, they may be more amenable to batch fabrication than magnetics. They also provide opportunities for isolation with multi-port resonators. But perhaps most importantly for our purposes, they have very high quality factors, which is good for efficiency, as well as very high power density capabilities. Now, piezos were used extensively a little more than a decade ago for lighting fluorescent lamps. And they've also been used in energy harvesting applications, like you see this shoe right here. But overall, piezos have still seen very little commercial use in power conversion, and attempts to use them in research without magnetics have shown limited performance. That being said, the most effective ways to use piezos and converters have yet to be explored. much less the full realm of potential ways. So to evaluate piezo-based converters for miniaturization, we're going to dig at that exact question today. How do we best utilize a piezo in a power converter? So we'll start by looking at what are all the possible switching sequences and topologies we can use. We'll then constrain those for high efficiency so we can start to compare them to figure out which ones are best. Finally, we'll go over some of our initial experimental results, and we'll wrap up with some unanswered questions for piezo-based converters going forward. To start, before we can design a converter with a piezo, we need an electrical model for it. This is a Butterworth-Van Dyke model, which is commonly used for resonators. It's got a physical capacitance, which is Cp between the piezo's two terminals. And it's also got in parallel with that an LCR branch, which models the mechanical resonance properties for the piezo. Now that we have a model for our piezo, we can start to think about what we would like to have in a piezo-based converter. If we believe piezos may be a route to high power density, we'd like to use them all by themselves inside of a converter without any additional magnetic energy storage that might bring down the converter's overall power density. So we're going to use the source load system shown on the right. It's got just the piezo, and we haven't specified anything about switches yet. Now we'd also like to soft charge Cp, and what we mean by that is we'd like to always charge and discharge Cp through resonance so we can reuse the energy it stores rather than lose it when we're changing the piezo's terminal connections. In addition to that, we'd like to be capable of efficient voltage regulation, meaning we'd like to be able to span a wide range of input to output voltage conversion ratios without much efficiency penalty. And finally, we need the required switch implementation for this converter to be practical, as simple as possible in order for piezo-based converters to be marketable. Now, keeping those goals in mind, we enumerate all the different ways we can use the piezo in the source load system, starting with its connections. Now, we're not thinking anything about switches yet, just what are the possible connections. And we're going to refer to each of these connections as a stage, and we'll look at each stage from the perspective of Vp, which is the voltage each stage puts across the piezo. So we'll start with what we call connected stages, in which we connect the piezo to the source load system so that Vp has some combination of Vin or V out across it. Vp could equal Vin, negative Vn, V minus V out. There's lots of options here. These are the energy transfer stages between the source and the load. Now we could also short the piezo's terminals in what we call a zero stage, in which we forced Vp to equal 0. And we could also leave the piezo's terminals open circuited. And this stage we'll call an open stage, allows Vp to change through resonance. This is where we would do that charging and discharge charging we talked about. Now we string these stages together to create what we call switching sequences. We can think of a switching sequence as the pattern of stages that we cycle through over and over again to pull energy in from the source, momentarily store it, and deliver it to a load. Now, one of our requirements is we always want to soft charge Cp, and so we're going to have to alternate our connected and zero stages with open stages in order to achieve that. So we'll look at an example here. In this sequence, let's say our first stage is Vp equals Vn minus V out. In this stage, if we've got a positive IL, we're going to transfer energy from the input to the output. At some point, we'll turn that off and we'll start an open stage in which a positive IL discharges Cp all the way down until Vp equals 0, at which point we'll start stage 3. At some point, the inductor current will drop to 0 in stage 3 and go negative. After that, we'll start stage 4 and use the negative inductor current to charge back up Cp all the way to V out, at which point we'll begin stage 5. And finally, we'll use the very end of our negative IL half to charge Vp all the way back up to V minus V out and start the process over. Now we're going to refer to these sequences by the order of their connected stage voltages. So we would call this sequence Vn minus V out, 0, V out, assuming the open stages exist between each one. This is going to be our example sequence throughout this talk. Now we might start to ask, well, what are all the possible switching sequences we could use in a piezo-based converter? To find that out, we could permute all these different stages and figure out all the different combinations, and then down select to the ones that actually meet the practical criteria we listed before. So the result of that is the 6-stage sequences you see listed here. There are 5 step-down and 5 step-up versions of these. All of them require only the piezo for energy storage. All of them always soft charge CP, and all of them are capable of efficient voltage regulation. On top of that, each of these can be realized with 1 or more practical topologies, which I'm going to show here. Each of these topologies consists of 4 unidirectional blocking switches, some of which may be implemented with diodes. This is on par with the switch practicality of many other common converters. Now, many of these converters are mirror images of each other. Some look like other converter topologies for switch capacitors or resonant converters. But these are the topologies that are needed to realize those switching sequences. Okay, now that we have a set of switching sequences and topologies, we'd like to constrain them for optimal behavior so we can start to compare them. Efficiency is one of our biggest considerations when choosing a converter implementation. So we would probably like to constrain for additional high efficiency behaviors. Now our switching sequences have already been constrained for soft charging. That was step 1 listed here. But we might also like to constrain for all positive instantaneous power transfer. And what that means is at no point in the cycle are we going to be shoving energy back into the source or pulling it back out of the load. Also, we might also like to constrain for soft switching or zero voltage switching on all of our switches. In reality, switches have capacitance between their drains and sources that stores energy when there's voltage across the switch. So similar to the piezo CP, we would like to charge and discharge these capacitances through resonance to reuse the energy they store. Now to do that, we need to resonate switch voltages to 0 volts before we turn that on. So we call it zero voltage switching. Now, in order to accomplish any of this, we first need to understand what's happening inside the piezo itself. And we're going to look at that with an example switching sequence, Vn minus Vout, 0 Vout, with Vout a bit less than half of Vn. That switching sequence requires the topology you see here. Now we're going to visualize what's going on during each stage of the switching sequence using state planes, which you can think of as roadmaps for the piezo state variables. We're going to plot one value of a variable against another and not worry about time here. Now each stage has its own VP requirements and IL direction. So for stage 1, for example, we're going to say VP equals Vn minus Vout. And if IL is positive, then energy is going to flow from the source to the piezo and to the output, like shown in this diagram. That's going to result in the following state plane trajectory, where on the left state plane, we see VP fixed at a constant Vn minus Vout, but IL rises. And then on the right state plane, we see IL resonate in an arc with VC. Now, without going into too much detail here, we can craft the state plane stage by looking at these constraints. Those constraints dictate what the trajectories are going to look like. And finally, we're back where we started. Now, requiring that the piezo states end where they begin means that we're constraining for periodic steady state. That means every single cycle, the piezo state variables are going to take the same exact path around the state plane. From here, we can start to constrain for the positive behaviors we want in terms of efficiency. So the state plane on the left gives us good insight into how the piezo interacts with the source load system. And as you can see here, we've constrained for soft charging, meaning we're always resonating VP to its next stage voltage before that stage begins. And if you were to look closely, you'll also see that we've constrained for all positive instantaneous power transfer. Now the state plane on the right tells us where we are in the resonance cycle at any given time. And so we can actually use the proportion of the cycle that each stage comprises to calculate what our switching times need to be. Now, in addition to this, if we decide that we'd like to constrain for soft switching or ZVS on all of our switches, we can use the state plane to better understand how we would need to alter the switching sequence to achieve that. In this particular case, we needed to alter our 6th stage. And so we needed VP to swing all the way up to VN at 0.6B for ZVS turn on of S1. So now that we've constrained the state plane, it can tell us a lot of information about what our time domain waveforms should look like for these high efficiency behaviors. Each of the stage transition points are numbered on the state plane, and these correspond to the number of dotted lines you see in the time domain waveforms. So even if we can only measure VP experimentally, we can still get a really good idea of what VC and IL might be doing based on whether VP is increasing or decreasing and its slope when doing so. Now, if we plot out the efficiencies of each switching sequence constrained for these positive behaviors, we see that there's quite a bit of variability between the sequences themselves. Now, the highest efficiency sequences tend to better utilize the piezo's resonance cycle for energy transfer. So they spend less of the cycle in trivial stages like 0 stages and open stages. These switching sequences are the ones we should choose in that case for high efficiency converter design. Now that we've learned how to best utilize the piezo in a power converter, it's time to actually build a converter. But before we do that, we need to find a piezo. For our first prototype, we sought low frequency piezos close to 100 kilohertz for the ease of control. And we also sought high mechanical quality factor materials for the efficiency applications. Now, piezos can be difficult to source, but the one that we found to be best for our purposes is a modified PZT material, 114 kilohertz radial resonant frequency. And so we operated it in its radial vibration mode. And it has a mechanical quality factor of 1500. And that's actually an order of magnitude higher than a lot of magnetic components. So we take this piezo and we built a pretty simple prototype with it. This is just a 2-layer board. It's got GaN FETs, Schottky diodes, and everything you're about to see here is an open loop operation. Now, when we run this prototype in the real world now, we're getting waveforms that match very closely in form with our expected waveforms for the switching sequences we want. Now, this top set of waveforms here are the simulated waveforms. The bottom set are the experimental. The similarities we're seeing here are great news for being able to use these switching sequences to get the high efficiency behaviors we desire. In each of these waveforms, we're seeing VP always resonate to its next stage voltage, meaning we're getting soft charging of the piezo. We also see all of our switch nodes resonating to their next stage voltages, meaning we're getting soft switching. And based on how VP behaves, we can infer that we're also getting all positive instantaneous power transfer. So this particular operating point has an efficiency of 97.1%. Now, if we look at our experimental waveforms as we change voltage conversion ratio, we see that our 0 stage increases in length. In this top waveform here, we see our 0 stage is almost non-existent. And that's because we're at a conversion ratio very close to 0.5. But as we decrease that conversion ratio, we see our 0 stage become much more dominant. This is how a 6-stage switching sequence regulates its voltage output. Now we can plot this prototype's voltage conversion ranges as a function of frequency to map out the converter's whole operating region. Now this is not purely frequency regulation. Each of these points have been tuned specifically for the switching sequence characteristics we want. But we see that as this converter can span quite a wide range of operating points while still achieving the high efficiency behaviors we want. Now here we plot efficiency versus power for a variety of set-down ratios below 0.5. And we see that efficiency tends to decrease as gain does here if we look at the general trend. But overall, we can get a decent range of good performance across a wide range of power levels. Now the downward spikes we're seeing here occur at spurious frequencies, which are caused by imperfections in the piezo's manufacturing or how we've mounted it in this first prototype. Now, if we look at how efficiency varies with power for gain greater than 0.5, we find that the gain has no impact on efficiency. at a fixed VN, and we can get an even wider range of power levels with good performance. This is great news for regulation purposes. Here we can span a gain range of 2 with essentially no change in efficiency. And it's worth pointing out that our peak efficiency here is above 99%. That's much, much higher than most converters. So at this point, we've shown that piezo-based converters can achieve high performance through effective utilization of the piezo. But there's still a long road of development ahead for miniaturization. Some unanswered questions include, how would we choose a piezo? What are the best geometries, best materials? Or how would we institute closed loop control to get all of our high efficiency behaviors? We'll take a closer look at that one. The behaviors we want require elements of all 3 of the different control schemes you see here: modulating frequency, modulating pulse width, changing dead time. All of those together are pretty difficult to implement. We might also ask, well, what happens when we scale up power? Or what happens when we scale up frequency? The resonant frequency of a piezo depends on its geometry, specifically the length of the piezo's length and the direction that it vibrates. So here I'm showing that for a thickness vibrational mode. And as the thickness decreases, our frequency increases. So this is definitely something we would need to do in order to miniaturize a converter, is we would need to drive up the piezo's frequency. In addition to that, we might ask, well, how are we going to handle high step up or step down ratios if our efficiency starts to go down? Or how would we get isolation? It turns out that both of those needs may be able to be met with what we call piezoelectric transformers. Piezoelectric transformers are 2-port devices that typically have ports along different dimensions of vibration, but there's also other ways to do it. And in addition to the advantages of the resonators or single port devices, they can provide isolation as well as an inherent voltage conversion ratio, which you see down in the electrical model shown at the bottom. So with that, we can conclude that we can design a converter based on a single piezo with high efficiency behaviors like soft charging, 0 voltage switching, and all positive instantaneous power flow, but also practical characteristics like voltage regulation capability and practical switch implementations. But the big take-home point here is that it's the effective utilization of the piezo that enables the competitive performance we're seeing with no additional energy storage components. And I should emphasize that the piezo we use in this prototype is just an off-the-shelf part. So we could expect to get even better performance if we actually optimize the piezo itself. Now, in terms of miniaturization, this is one step in a long process of development that's going to have to happen. But we do believe piezo-based converters are promising and that they may in fact open new application spaces for power electronics. With that, I'd like to acknowledge our sponsors, Texas Instruments, NSF, and the Masdar Institute Cooperative Program. Thanks for your support, and thanks for your time.
Are there any specific questions that the audience would like to first of all bring up? If so, you can do so by either sending a chat or by raising your hand, and I will call upon you. I see John Kasakian has raised his hand. So John, please take over and ask a question.
Great. Jessica, great presentation. In spite of the few glitches, you did a marvelous job with it. And I'd like to talk to you a little bit after you're freed up about the mechanism you use, because I have a challenge with Zoom at the moment that I'm not quite sure how to deal with. But my question is, you did not indicate the frequency at which you were operating your experimental system. I assume it's at the radial frequency, the radial resonant frequency of the piezoelectric resonator. Is that correct?
So it's not directly at the radial frequency, but it's very close. And in fact, it's slightly above the radial frequency, because at that point, we're operating in our inductive region for the piezo. There's a very narrow inductive region. And so operating in that region is what enables us to get the soft charging and the DBS.
I see.
And so to quantify that, if that's what you were asking, yeah, we were operating probably between about 118 kilohertz to up to 125 kilohertz. So very low frequency for now.
Right. Thank you.
Thank you.
Ali, there is a question in the chat. Would you like to just unmute yourself and ask it directly?
Sure. Let me put my video on as well. Okay. Great presentation, Jessica. Thank you. We have used piezo technology in 3D MEMS-based optical switches that are currently being used at layer 1 of data centers. And it has very good performance. I was wondering whether your innovation adds anything new to today's state of art on piezo.
I'm sorry, could you repeat one more time? I'm having some trouble hearing.
Sure.
So Ali, the comparison between a MEMS-based optical switch and a piezo switch, you're trying to see a value of the piezo material being inserted inside the MEMS type structure. Is there a side-by-side comparison you can make between piezos and MEMS?
Yeah, so in terms of optics or anything like that, I can't speak for those specific applications, but in power conversion at least, piezos tend to give us a really good combination of both power density and efficiency. And so in terms of other MEMS devices, we haven't explored as much just because perhaps fundamentally there doesn't appear to be an immediate advantage there. That doesn't mean there may not. It just, piezos are what have stuck out so far to us.
There is another question just came in, first of all, by starting by saying, thanks for a great and clear presentation. And then second, the question itself is, have you considered the dielectric loss when adjusting switching frequency?
That's a very good question and a very good point. So we have not looked into that specifically for this prototype, but dielectric loss is a major component that will need to be considered as we go to higher frequency, as we go to higher voltages. So what I was showing in this presentation was essentially just a mechanical loss in the model that we showed. But for everyone else, in reality, across the capacitance, there's also leakage through the dielectric of the capacitance in which we're going to lose energy the capacitance is storing. Not in detail, we have not looked into that, but we certainly need to.
If I may also add another question, the voltages that you are operating at, you have shown us that as you get to higher voltages, you get even higher performance responses, meaning the efficiency keeps improving, which is wonderful. At the same time, miniaturized electronics, right, you would imagine would be used in portable type applications. So is there a limit to the how high the voltage should be from perspective of a user handling this particular miniaturized system? Or is that simply not the case, because really what you would do is use these in more isolated systems like nanosats or MRI systems?
Yeah, so I think there's two questions there that I'll attempt to answer. So the first is that well, okay, so I guess the first point I will make is that the piezos themselves like high voltage, low power. And so that dictates what applications we would want to put them towards. So it's likely that the very low voltage, tiny stuff may not perform as well with the piezo. Now, in terms of consumer electronics or anything else, the piezo is not going to necessarily dictate what voltages we're using. It's just going to be a matter of, does the piezo fit what our voltage need is there? And so it's certainly will be a trade-off in the low voltage situations on whether or not we need to use something like this or whether a different solution could be better. But the high voltage, low power is where this would shine.
Well, Jessica, again, thank you for a fantastic talk. I very much look forward to seeing all of you next week when the Nano Explorations continues. Jessica, again, thank you today.
Thank you all so much for coming. Appreciate it.